Log on, tune in, find out. Another good idea from Cambridge.
Okay, so yesterday we were talking about vector bundles, and today we will talk about the principal bundles, which are generalizations of vector bundles. Okay, so then if you remember yesterday, a vector bundle, there were two important things about the vector bundle. So it was a projection, and it was locally free, locally trivial. So there is some locally, it is just a product. And the fiber, well, I will say this. So the fiber is just a vector space, so the automorphism group is a GLR. So actually it is more important this than this. So what is really important is that we have some fibrations in which the fibers have some automorphism group, which is a GLR. Now for a principal bundle, we just want to replace this with another group G. So we will have to think what kind of fiber to put to obtain this. And again, we want some fibration which is locally trivial. But for some reasons that I will explain, here it was enough to look at the Zariski topology, but now it will not be enough. We will need to look at the et al. Topology. So I will explain briefly what is et al. Topology. Well, if I were doing a differential geometry, then I could take just the analytical topology. But since I want to do this in algebraic geometry, I have to consider this. So an et al. Topology is an example of what are called the Grothendieck topologies. So this is a generalization of the notion of topology. In fact, a Grothendieck topology is not a topology in the usual sense. So the idea is the following. So what is a topology? To give a topological structure to some space, we give some open subsets, a collection of open subsets which satisfies some properties. The idea of a Grothendieck, and so an open subset, I can think of just some injection. The idea of a Grothendieck is that we are going to look at the maps, but I am not going to require the maps to be injective. So an open subset in the Grothendieck topology is not even a subset. So this looks like a very crazy idea, but actually it works. Well, in the case of the et al. Topology, then an open subset, the role of the open subset is going to be played by et al. Maps. So an open subset in this topology is just some et al. Map to our space. Okay, so then now I am going to see that this is useful, that what I do with usual topology, I can also do here. So for instance, what kind of things do we do with a topology? Okay, so maybe we have the space, we have some function, some complex value function, and I want to restrict to the open set. Well, this can be defined just as the composition. So then by some slight abuse of a language, I can even use the notation of a restriction. This is just a composition. Then, another thing that I can do, suppose that I have some projection into X. And I have here an et al. Open set. How do I define the restriction to the open set? Well, it is clear. I just take the Cartesian diagram. And again, by abuse of language, I use this notation. Okay, what about intersections? So if I have one open set, one étal covering, another étal covering, I define the intersection as the Cartesian product. Okay, so if these were actually subsets, then the Cartesian product is just intersection. So this generalizes the notion of intersection, and so it works. And if this is étal and this is étal, then this is also étal. So it is again an étal open set. Well, one word of a caution. In the case of the étal topology, the intersection of a open subset with itself is not itself, because, so suppose I have U and here again U. Suppose this is an A to 1 covering, this is an A to 1 covering, then this is an A squared to 1 covering. So the intersection is not U itself. But well, it doesn't matter. I can still work with this. Okay, so then all this is very easy, but now we come to the difficult part. The difficult part is the following, that so something else that I want to do with the topology is to glue, to be able to glue. Because, for instance, suppose that also, well, for sheaves, I can restrict the maps and I can also restrict the sheaves. If I have a sheaf here and I have an open set like this, then this I will call, well, F, let's say. So this is what I can think of as the restriction to the étal open set, right? Okay, so now I will have the following situation. Suppose here I have some sheaf on U1, some coherent sheaf on U1, some coherent sheaf on U2. Here I have the intersection. So then I have the restriction to this intersection. Well, I will call this a V. So this restricts to this, and this restricts to this. Suppose I am given an isomorphism to glue, to make the gluing. So if these were open subsets, usual open subsets, if I have two sheaves and I have an isomorphism on the intersection, I can glue them and I get a sheaf on the whole, on the union of both of them. Here, well, I will suppose that the images of one E1 U1 union image of U2 is equal to X. So U1 and U2 is a covering of X. Okay, so then if I am given here an isomorphism, what I want is a sheaf here such that this and this are the pullbacks of the sheaf here. So this gluing, it is difficult to prove that you can do this, and it goes under the name also of descent theory. Because since this is a covering, what I am doing is that this sheaf that lives here, I want it to descend here. So I want this sheaf to be the pullback of something here. This is why it is called the descent theory, but I can also think of it as a gluing in this generalized topology. And also I will have to glue fibrations, not only sheaves, but also fibrations. But well, all this can be done. And actually, when you work with the étal topology, to a large extent, you can forget that it is a generalized topology. When you work on it, it is almost as working with a usual topology. Okay, so now we are ready to define what is a principal G bundle. So G can be any group, but well, for simplicity, I will work with an algebraic algebraic group over C. And actually, I will mostly be interested in reductive groups, especially when I construct the moduli space. But the definition is general. So a principal bundle or principal G bundle over X is a projection pi over X. G acts on P, so there is a right action of G on P such that pi is G equivariant, invariant, sorry. So the action is fiber-wise, and locally, so there exists covering by et al. Open sets such that P restricted to UI is isomorphic to UI times G. This projection is just a projection to the first factor, and the action, the G action, is just a right multiplication on the right, here. Okay, so well, then there is a notion of a isomorphism. So P and P prime are isomorphic if there is an isomorphism between them, and which such that alpha is G equivariant. Okay, so the best way of thinking about this is the following. So here what we are actually doing is that we are doing a fibration again, which is locally trivial, and on the fibers, what we are putting on the fiber is a G torsor. So don't think that we are putting a group G, the group G here, and that is not a good idea, because a group should have a one distinguished element, which is the identity. But when I do the gluing, since the gluing, or I didn't talk about the gluing. Okay, so yeah, I forgot. Yeah, on the intersection. So if I have Uij intersection Uj, intersection in the sense of the tau topology, but I use the notation of the usual topology, then if this map is psi I, then phi ij, which is phi I minus 1 composed with phi j, this goes from I g to I, well, ij times g. So this should be G equivariant with the multiplication on the right here, and in particular then this has to be defined, this is just a multiplication on the left, so that it commutes with multiplication on the right. So this actually is defined by some map from the intersection to G, which is going to define a cocycle. Okay, but then the important thing is that here, in this transition function, the identity is not respected. So then, abstractly, in this fiber, there is no distinguished point, which is the identity. I have forgotten which was the identity. But I have a global action on G. So then a space like this is actually a G torsor. And So I have chosen a G torsor because the automorphism group of a G torsor is exactly G. So this is the important thing about the principal bundle, that the fiber, the automorphism of the fiber is G. Okay, so as I was saying, these gluing functions, they satisfy a cocycle condition. On the other hand, if I change the trivialization psi I and I take another trivialization, these transition functions will change by a coboundary. Then finally this defines a class in the Czech cohomology with values in G. So yesterday for vector bundles, here we have the GLR. Okay, so now I will give some constructions with principal bundles. Suppose I have a G acting.
What does that Czech cohomology mean?
So you mean the group? So this set, sorry, it is not a group, it is a set.
But it's still okay, all the colors of the Tal topology.
Yes, 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 this is a Tal, yes. I'm taking coverings with a Tal topology, and then I will have to take the limit of a finer and finer coverings. And yeah, also it is important, this is only a set. It is a distinguished, it has a distinguished point which corresponds to the trivial principal bundle, but it doesn't have, in principle, any further structure, just a set. Okay, so suppose that G is acting on on a scheme F. So G, there is a map to the automorphism of that fiber. Then and P is a principal G bundle. I define the associated fibration as follows: P times F, I take the product, and then I divide by the action of a G. So this means G acts here and here, here on the right, and here, well, usually I will take left actions. Yeah, so this is acting. With a left action. So then basically what I am doing, I am taking another fibration, but the fibers now are copies of a G. Okay, so then now the extension of a structure group. Suppose I have a homomorphism between two groups, and P, suppose it is a G bundle, principal G bundle. Then I define the extended principal bundle, which is going to be an H bundle. And again, I do it like this. Here, the action of a G, this is a particular case of this situation, where since I am given this map, G acts on H by left multiplication, so that I have a left action, and then this thing here maps to X, projects to X. There is still a global right action of H here, and so this is an H bundle. From the point of view of cocycles, it is very easy to see what we have done, because so the G bundle will be given by a cocycle like this, and so I just compose with H, and I get a cocycle for the H bundle. There is no need for this to be injective. In many occasions, this will be an injection, for instance, the orthogonal group inside the general linear group. And then this is why this is called an extension, because you are extending to a bigger group. But the definition works for any homomorphism, and it will be used for many other homomorphisms. And then there is the opposite construction, which is the reduction of a structure group. Again, I have a homomorphism of groups like this, but now what I am given is, well, an H bundle. So this is going to be the opposite construction. So I want a G bundle whose extension is P. So a reduction is going to be actually a pair consisting of a G bundle together with an isomorphism with the extended original bundle. This you have to be careful, because sometimes reduction is called only to this bundle. Sometimes it is called to both the bundle and the isomorphism. Of course, there is always at least one isomorphism, but so the way to distinguish the two situations is the following. So what is
Have you pushed forward the red bundle there?
Yes, the wrong. Yes, thank you. Yeah. Okay, so what I was explaining about whether this is given or not is so you can distinguish if you look at what is the notion of a isomorphism between reductions. So an isomorphism between two reductions for me is going to be, so if I have a principal G bundle and another, so one reduction, another reduction, so an isomorphism will be an isomorphism between the G bundles such that the this diagram is commutative, and here I put the associated isomorphism. So depending on whether you require this or not, then this is how to tell whether this is just a datum extra data or not. Okay, again, the name reduction comes from the case in which this is just a subgroup of this, and then you are reducing to a smaller subgroup, but the definition works in any case. But if it is...
There's no condition involved, it's the group. It's not a group homomorphism.
No, it's a group homomorphism only. In principle, for any group homomorphism, you can define this. Okay, so okay, well, if rho is injective, a reduction then giving a reduction is equivalent to giving a section of this associated vibration. So the subgroup is G, so I will have here so I divide by an axion on the right, so that this has still a left axion, and I take the associated vibration. So a section of this, so will be a section like this. Yeah, it's okay. So for instance, suppose rho is the orthogonal group inside the general, well, OR, inside the general linear group. Then GLR divided by OR, this is the set of bilinear non-degenerate symmetric bilinear forms on the vector space CR. So then giving this section is to give in the generate bilinear form on its fiber. So if E is the vector bundle corresponding to the principal GLR bundle, then this section is just to give a bilinear form like this. So this is the reduction of the structure group. Okay, for the symplectic group, the same is true, instead that here I have a skew symmetric. Okay, so okay, so something that I have already mentioned, but I haven't explained, is that so I am going to look more carefully about the relationship between vector bundles, as I defined yesterday, and GLR bundles, to see that they are not exactly the same thing, but they give equivalent categories. So if I have a vector bundle, as yesterday, so the fibers are vector spaces, then I can construct the following. P is going to be the union, this is going to be the frame bundle, it's called. The frame bundle means that I take the union of the basis of the set of bases of each fiber. So this maps to X. I can give here a nice algebraic structure. So this is just a set theoretic description. Here, of course, GLR acts here because if I am given a basis, a choice of basis, and a matrix in GLR, I get a different basis. So this is actually a torsor, a GLR torsor. So in this way, from a vector bundle, I get a principal GLR bundle. And in the opposite direction, if I have a principal GLR bundle, of course, GLR acts on CR. And then the associated fibration is just a vector bundle. This gives an equivalence between categories. And so this is why when we talk about the vector bundles or principal GLR bundles, we change between the both points of view. Okay. Okay, so now I will give another example of a reduction. So there I explain what is a reduction when rho is an injection. If rho is not an injection, then I have to look carefully, case by case, what I should do. But
So in the classical sense, it's an equivalence of categories. But if you're working with the entire topology,
yes, because okay, yes, this is okay. The reason I didn't use a tall topology for a principal for vector bundles is that it is not needed. But I want to, if I want, I can make the definition with étale topology. What happens is that a principal GLR bundle, if it is locally trivial in the étale topology, it is already locally trivial in the Zariski topology. This happens for a GLR and for the symplectic group and, well, some combinations of them. So there are a few groups for which this happens. But already for the orthogonal group, this doesn't happen.
And in this construction, you make the fiber on the right is GLR and the fiber on the left is CR.
Yes. Yes. Well, to be more precise, the fiber on the right is GLR torsor. It is not GLR, so it's the set of bases of a vector space. If I just say set of bases of a vector space, there is no distinguished bases. They are all equal. If I say GLR, then there is one that is distinguished. So this is the difference between a group and a torsor on the group. Okay, well, then another case in which I have a nice description is if the group is PGLR. Then PGLR bundles, the category of PGLR bundles is equivalent to the category of PR-1 fibrations. Well, I won't write the details, but you can do something similar to what I have done here. So the important thing here is that so every time that I have a group, then I can consider the principal bundle because I have some fiber which this group as an automorphism group, which is the G torsor. But if there is some other nice space which has G as a automorphism group, then there is an equivalence of categories of fibrations with these fibers. So for GLR, I can consider vector bundles. For PGLR, I can consider projective fibrations, and so on. Okay, so then now I will give one example that uses this. Yeah, suppose I have a PGLR fibration that I am going to think using this equivalence as a fibration of principal bundles. Now I have the group going from SLR to, well, PSLR, which is the same thing as PGLR. Or, well, yeah, no, better this, to make it simpler, GLR going to PGLR. And then I want to give a reduction to GLR. So what is this? So it should be a GLR bundle, this means a vector bundle, such that the extension is isomorphic to this. So a reduction to GLR is a vector bundle together with an isomorphism of the projectivized bundle and the original projective bundle. Okay, then the set of all reductions is a peak X torsor. So peak is the Picard group, the group of line bundles. And this means that if I am given two different reductions, they differ by a line bundle. Yes, of course, because if E is a reduction, then E tensor L, so P of E is canonically isomorphic to P E tensor L. So if I tensor, I I get a different reduction. Okay, so now an exercise. Suppose I have this. So, what is a reduction of a vector bundle to an SLR bundle? So, since it is an injection, then it should be a section of something. So, this is the exercise, easy exercise. Okay, so now what I want to do is to give a sketch of how we go about the construction of the moduli space of principal bundles. And for this, I have to introduce an object. Well, the construction of the moduli spaces, first some history. It was first it was done by Ramanathan for the case of a curve, and then well, there is several people which has worked on this: Adrian Langer, Alexander Smith, Ignacio Sols, and myself. So first we were working in parallel, and then we have some work together trying to generalize this for characteristic P. Okay, so then the description that I am going to give is what I did with Ignacio Sols, which is a generalization of the work of Ramanathan, generalized from dimension 1 to higher dimension. So then we have to introduce a new object that we call a tensor. So a tensor is a torsion-free sieve in general. Together with a homomorphism with some A factors. Okay, so if you want, this would be another example of an augmented bundle. So this would be a generalization of what Norbert was explaining. Here, something that is an extra difficulty is that this is a nonlinear object. This is going to give us a lot of trouble, but well, we can work with this. Okay, so then
What is the superscript you put over that bracket?
A.
Oh, I see.
Yeah, it's A. So just some A copies.
I thought it's a G.
Yeah. Okay. No. Okay. So then, to define the stability for this object, I have to consider filtrations, weighted filtrations. So a weighted filtration is something like this: some filtration indexed by some weights. With increasing weights. Actually, everything that I say about the weighted filtrations, it can be also rephrased with Z-indexed filtrations. So a Z-index filtration is just a filtration in which I have elements for all integer numbers, but here I have to allow for equalities. Here I remove the equalities. Okay, so just to give an example that this is the same, suppose I have a filtration of the first type, like a -2 inside 0, then, and well, this continues, then what I do is I just put enough copies for all integer numbers. So this will become a Z-index filtration in which there is a jump only on the weights, which are integer numbers. So this is just some bookkeeping. But well, sometimes the formulas are easier if I put them in one way or the other. Okay, so then the notion of stability is the following. So I have to define some number for the tensor, some mu, which depends on the tensor and on the filtration, and this is the minimum of lambda I1 times lambda IA, such that the restriction is different from 0. So this is just some number which depends on the field, the tensor phi, and the filtration. I call the filtration, well, here, balanced filtration means that is equal to 0. Well, the geometry that is behind here is that a balanced filtration is, so any filtration is produced by a one-parameter subgroup of a GLR. A balanced filtration is produced by a one-parameter subgroup of a SLR. This is the reason for this condition. Okay, so now I fix a polynomial delta of degree well, actually, usually I will choose the degree to be equal to the dimension of x minus 1, but yeah, I could take also smaller or equal, but what I get is not very interesting, so it is better to fix this idea. This is going to be the parameter. So if I were in dimension 1, then a polynomial of degree 0 is just a number, and this is the parameter that appeared on Norbert's lecture. And then the definition, a tensor is delta semi-stable if for all balanced filtrations the following holds. And this is this number that they have just defined. And this should be, as usual, strict inequality for stable, and I allow equality for semi-stable. These are the polynomials that I defined yesterday, the Hilbert polynomials of the corresponding shifts. So this is a polynomial, and the equality means asymptotic inequality. Okay, so then this is a complicated notion. One thing to consider is that, so usually for stability, you check stability looking at the subobjects, subbundles, subsieves, things like this. But here you have to look at the filtrations. It is not enough to look at the subobjects. This is one of the difficulties that we are getting because we are working with an object which is intrinsically nonlinear. Okay, but so this is the general notion, but when I have tensors, we have some geometric meaning, very often this gets simplified. And I will look at some examples now. So I leave here the general definition.
Excuse me?
Yes?
What is delta doing?
Delta is a polynomial
Yeah.
which is multiplied by some number. So yeah, this is a degree n-1 polynomial multiplied by the number. Okay, so maybe I should put the number in front of the polynomial. So that, yep.
Maybe now I'm confused about the inequality.
Okay, so this on the left-hand side, I have a
anything into the polynomial. I mean, what does it mean for the polynomial? You mean for all values of the polynomial? It's
no,
negative?
no. For m, so I say that the polynomial is so if well, I will call f is a polynomial. Then I say that f is smaller than 0 if fm is smaller than 0 for m large enough.
Sorry, and you said this delta is like which of Norbert's
The parameter that so for the notion of a stability of the objects that he was considering, he introduced the parameter, and then at the end he was explaining how the moduli space changes when you change the parameter. Yes, 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 he called it alpha. Yeah, so if he was working on a curve, so then for him it would be a degree 0 polynomial, so just a number. So it would be just alpha.
Did you get this just by going through GIT? Or?
Yes, yes, yes. This comes from a GIT. I won't explain what is the construction. The construction is inspired in the construction of a Hoiberts and Len of a coherent shifts, or coherent. I think they call them. Well, I forgot the name. But basically, what they are doing is that they are just taking a equal to 1. The case a equal to 1 was done by Hoiberts and Len, and we followed their techniques. Okay. So then let's see one example. An orthogonal sheaf. So an orthogonal sheaf is going to be a torsion-free sheaf, E, together with a bilinear form. So this is just a torsion-free sheaf, and well, I require that this is symmetric and non-degenerate in the sense that the associated homomorphism between the determinants is an isomorphism. So this means that at the points in which this is locally free, this is given a non-degenerate bilinear form. Okay, so now if E prime is a subsieve, I define the orthogonal complement just as the kernel of E dual, E prime dual. So this is the map induced by this. And then I define a notion of stability for orthogonal sheaves that later on one checks that coincides with what I said there. So the notion is the following. This is semi-stable if for all orthogonal filtrations I will explain in a moment what this means. This holds. And an orthogonal filtration is called orthogonal if the orthogonal complement of the piece I is equal to this. So if I have the filtration and I take the orthogonal complements, I swap all the elements. And well, the proposition is that so this is actually a tensor, so it makes sense to take the definition of that I have there. So this is semi-stable as orthogonal sheaf is equivalent, so if and only if delta semi-stable as tensor as long as the degree of delta is exactly n-1. Okay, so then this is an example. So sometimes you have some parameter when you define the notion of stability. In principle, you have some parameter, but in some situations, even if you change the parameter, the actual stability does not change. And this is one of these situations, as long as you have this thing. This is equivalent, so requiring this would be the same thing as Norbert did when he imposed that alpha should be positive. Okay, so okay, so then with this, actually I have already, since I have constructed the moduli space of tensors, and an orthogonal sheaf is an example of a tensors, then and the definition, so the stability conditions coincide, then I have a moduli space for orthogonal sheaves. And since an orthogonal bundle is equivalent to a principal OR bundle, then I have that orthogonal bundle is equivalent to a principal OR bundle. So the moduli space of orthogonal sheaves is a compactification of the moduli space of a principal OR bundles. So then I have already one example in which I have constructed this. But this is, of course, a very particular situation, because for this group I have a very nice description. For other groups, so here, basically what I have used a standard representation of the orthogonal group. For a general group, there is no standard representation. So what we do is we look at the adjoint representation. Okay, so then this leads us to the notion of a Lie algebra sheaf. So a Lie algebra sheaf is going to be a torsion-free sheaf together with a homomorphism like this. Here I take double dual. This might look strange, but actually I have to do this. Okay, so this doesn't look like a tensor as I defined before, because everything should be on the left. But there is a trick for which I can convert this into a tensor. So if I use this natural isomorphism, double dual, and then I set E equal to, well, and I to this. So well, this is the other way around. If I have a F and I set E equal to this, then this homomorphism becomes a tensor like this. So with this trick, this becomes an example of what I had before.
I'm sorry, but E is not a vector band, no? Right?
No, it's a torsion-free sieve.
Ah, okay.
Yeah, but these equalities hold also for torsion-free sieves. Yeah, if you think a little bit, basically, yeah. Okay, so then, Lie algebra sieve definition is semi-stable. Well, no, okay, I have to say something. Well, I will call it see, if a G is a Lie algebra. Well, no, here yeah, I haven't finished it. So a Lie algebra sieve is something like this, but of course, I forgot to say that on each fiber in which E is locally free, this should give the structure of a Lie algebra. If this Lie algebra is always isomorphic to some fixed G, then this will be called G sieve. So a G sieve is a torsion-free sieve together with a map like this, such that on the points in which this is locally free, the Lie algebra structure which I am producing is isomorphic to this fixed G. Now I will assume that the G is semi-simple. Then the Killing form produces a bilinear form, an orthogonal structure. This, I can define this on the points in which it's locally free, and then it extends uniquely to homomorphism on the whole. Okay, so now I can define this notion. So a G sieve is semi-stable if for all orthogonal algebra filtrations the following holds. The numerical equality is always the same. Orthogonal filtration, I already said what it means. Algebra filtration means that the EI, EJ is inside EI plus J double dual. And again, proposition semi-stable as G sieve if and only if semi-stable as well if and only if delta semi-stable as a tensor, again when the degree of delta is exactly equal to the dimension of x minus 1. Okay, so then with this, since the automorphism group of a G sieve, okay, so then with this, So G band. Yeah. So this, if this is locally free, then this corresponds, is equivalent to a principal bundle with this group. So the moduli space of these G shifts is a compactification of the moduli space of principal bundles for these groups. Basically, with this, I can get, well, these groups in general, they are not connected. Well, yeah, basically with this, I can get all the groups of adjoint type. And then the final step that I have to do is that if I have a group which is not of adjoint type, I do this trick. So this is the group. I divide by the center, then this is of a adjoint type. Then I know how to treat this group of a adjoint type, and then I will have to give a reduction. This requires some work, but it can be done. And as a further comment, the stability. So one can do the GIT quotient without changing the notion of stability. So in other words, the stability of a principal bundle only depends on the stability of the associated principal bundle for the adjoint group.
In your definition of semi-stable, should it be RIPE?
Yes. Yes. Thank you. Okay, so well, in the case of a curve, there was already a notion of stability for principal bundles, which was given by Ramanathan, and one can check that this definition coincides with his definition. Basically, in the case of Ramanathan, he is considering reductions to some parabolic subgroups, but when you have a reduction to a parabolic subgroup, then you get a filtration of the adjoint bundle. And these filtrations are the filtrations that we are considering here. Yeah, in other words, if a filtration is orthogonal, is an orthogonal an algebra filtration, then you can show that it comes from a reduction to a parabolic subgroup. And then the numerical condition that we give also coincides with the numerical condition that Ramanathan gives. Yeah, okay, so this is everything.
Question? Do you get to assume X is smooth, or is that irrelevant?
Yes, X is smooth in principle. In our work, we are assuming that, and we need that in some steps. So it will require some work to lift that condition.
Right, so what is the problem with double dual?
So can you
Yeah. I'm saying, for instance, is the dual of a vector bundle in the entire topology itself?
Say it again? See?
Double dualization of a vector bundle with the entire topology give the same bundle?
Yeah, no, well, the topology doesn't play a role there. So if this is, yeah, so if E is a vector bundle, then the double dual is the vector bundle itself. So this is only because I'm considering torsion-free sheaves. So even more general, a sheaf is called reflexive if the double dual coincides with it. But in general, for a torsion-free sheaf, the only thing that you can say is this: the double dual is might be bigger than the original sheaf.
Can you then?
Yes. Just suppose that you have a point in X in some surface. Then take the ideal of the point. Then the ideal of the point double dual is just OX.
When you fix your polynomial delta, you want to assume its coefficients are non-negative.
Yes. At least the leading coefficient should be positive. Yes. So, in other words, using this notation, yeah, I forgot. So, with this notation, I have to assume this. Yes, thank you.
Where does the condition of balance filtration appears in the construction?
Because, yeah, ultimately it appears in the when you check the stability with the Hilbert-Mumford criteria. There you have to consider one parameter subgroups, but these one parameter subgroups should be subgroups of SLR.
There are no more questions. We thank you.